Okay, so we're going to get started. My name again is Steve Case with Electro, and welcome to our Overcoming Validation Challenges with PCIe 6, DDR5, and 800 gig bus implementations. And today our presenters are all from Keysight, so we'll get started with some introductions. Good morning, everyone. And so our presenters today are Brig Assay. He's a Director of Strategic Planning and Internet Infrastructure with Keysight, and he's going to lead us off with some introductions to the topics. But we also have Randy White. Randy is the Memory Solutions Program Manager at Keysight, and he will be discussing some DDR technologies. And we also have, there's Brig and Randy White. And we also have Rick Eads. And Rick is not with us today, and most of our guests here today are actually with standards organizations, and John just got off of a standards organization meeting, and Rick is in one. So Rick has recorded some things for us this morning, but Rick is involved in PCSIG, and we'll be talking about PCIe 5 and 6. And John is a senior strategic planner for wireline solutions with Keysight. And we have a little program set up for everyone. But before we actually get into that, I'd like to thank Mark Erickson from Keysight, who kept us all on schedule here and organized and with the meetings. And also wanted to thank Madison Clark for helping us out and getting a lot of the other stuff organized. And so with that, I think, Brig, I'm going to pass it over to you so we can start the presentation. But right before we do that, I wanted to talk a little bit that we have our Electro commercial. Electro has $1.2 billion of test equipment inventory all over the world. Our main locations are in California. We have assets in London, China, Malaysia, and India. So no matter where you are, we can help out with the technology. And especially today, when we're talking about the high-speed technology, we're talking about Keysight BERTs, Keysight high-speed scopes, the UXRs. We have a fleet of UXR scopes go all the way up to 110 gigahertz. And we have BERTs from Keysight as well. And so with that, I think, Brig, I'm going to make you the presenter and let you get started on some introductory topics.
All right, sounds good. Thank you very much.
Oh, one thing I did want to mention is that we're going to have a questions and answers section of the webinar. And so if you do have a question, go ahead and ask, and we're going to get together and at the end of the webinar and see if we can answer any of the questions. Go ahead, Brig.
All right, so today we're going to be talking about three different topics, which is DDR, PCI Express, and then what's happening at the highest end, which is the IEEE and OIF CEI standards. And I wanted to kick this off just by talking about what's going on inside of the industry, and I'll be brief with my comments, but when you look at what's going on from the industry perspective, what you see is massive growth across, whether you're talking about even something as simple as a TV, all the way to the billions of devices that are out there. We continually see this growth that's happening, and this growth means the need for better technologies, for faster technologies, for technologies that can handle all of these new devices that are on there, and then all of the new applications that are happening on all of these many devices. And so when we think about it, you have these high user traffic devices that are happening. This includes autonomous driving, Bitcoin mining, analytics, and then on top of that, inside of the data center itself, you have these new things that are happening, like, or not new, but things that are happening like machine learning, artificial intelligence. You have virtual networking, and then you have this big drive to east-west traffic inside of the data center. And so you have this huge amount of need for data. And as a result of that, you have this need for new technologies to be driven, or new technologies to be added to help offset some of the demand for the data. So So when we look at it from the data center side, there's actually three different things that are really driving new technology. First off is power. So the idea of being able to drive less power is obviously critically important. I always use a story about, I grew up in a small town, Cheyenne, Wyoming, which is about 50,000 people. There was a new data center that was opened up about 5 miles outside of town. And the data center itself took more power than the entire city of 5,000 or 50,000 people that I grew up in. And so as we move forward, this idea of pushing down data or pushing down power becomes really important. And then the second thing, and this is a large part of what we're going to be talking about, which gets into capacity. How do we handle more and more data that's going through? Oops. And so capacity. So how do we handle more and more data going through the data centers? Obviously, we can continue to build data centers, but those are extremely expensive. If we can put more capacity through these data centers, then it only helps us. And then the final one is utilization. So we're spending all this money on capital inside of the data centers. How do we squeeze everything we possibly can out of those data centers? And so those are the things that we're looking at. The other thing that we have I don't know what's going on. The other thing that we have happening is inside of the data center, there's this move from what we were in a normal compute-centric server all the way out to what's known as a data center, data-centric server. And what this actually means is before, when we were looking at compute-centric, the CPU was kind of the central part of the entire server. And you had your DRAM, you had your hard drives, and you even had your smart NICs that were up here. And ultimately everything went into the cloud. But the big key here was the CPU. It was the thing that drove the server. Over time, then we moved into a little bit more, still compute-centric, but starting to think about data-centric. And this drove the need for more GPUs, and this actually was being driven heavily by machine learning. And so GPUs, FPGAs became more and more important. We saw a pooling of SSDs and hard drives that were out there. You still had your NICs and everything. And now as we move forward, in order to be able to handle this huge capacity of data, we're seeing this data-centric move. And this includes things like the new component called the data processing unit. You see now that the CPU is actually being pooled together as part of it and being driven by the data processing unit, SSDs, your hard drives. And so you actually have a brand new technology that's happening inside the server to help with all of these different technologies. And so you have your autonomous driving, you have your machine learning that drives this data, and then you have inside of the data center itself, you have new technology that's driving even down to the server itself. And so with that, that's what leads us to this next technology here, which gets us to the JEDEC, which gets us to where our presenters are going to talk about. And this includes Randy, who's going to talk about JEDEC and just the disruptions that are happening inside of JEDEC. We have Rick that's going to be talking about PCI Express 6.0 and just what that new signaling means from a technology perspective. And then, of course, John will be talking about 224 gigabits per second and just how that's pushing the various limits of signal noise ratio and everything else that's happening. And so with that, I will go ahead and turn the time over to Randy. So Randy, it's your turn.
Yeah, thanks for allowing me to join this presentation today. Just a quick introduction. This is Randy White. As Brig mentioned, I'm going to talk about some of the DDR challenges that designers are facing today. And I have the fortunate opportunity to have a front row seat in the JEDEC Standards Committee, and I'm witnessing a lot of the changes that Brig alluded to in the data center. More data disaggregation, compute moving over to data. When you look at the memory industry today from a validation and test perspective, this has evolved quite a bit. There's a number of aspects that we need to consider today. How does the protocol look? How do you gain signal access with superior probing solutions? Receiver test, this is something that's novel and new and been introduced recently. So I don't have time to talk about all of these today, but I realize and acknowledge that Validating memory today has gotten a lot more challenging, and the test solutions need to be much more efficient and make your job easier. So today I'll talk about transmitter test, receiver test, and then close with protocol. So to briefly kind of set the stage for where DDR memory has come and where it's gone today to DDR5 and moving into DDR6 in the future. Obviously, we have speed increases, higher data rate means you can transfer more memory between processors and your compute volatile memory, your SDRAM. So speed helps there, but there's also been in line with those speed increases some signal integrity and technical challenges that require a little bit different thinking in terms of testing. So previously we had things like setup and hold time. These are static timing parameters. Moving forward, we've picked up on the memory side, we picked up a little bit more of the SerDes test techniques like jitter decomposition, jitter modeling, and I'll cover in just a little bit more about actual bit error rate testing for the receiver. So let's go jump right into transmitter testing. I want to identify some, highlight some changes there. With the higher speeds, there's been more flexibility implemented for the receiver for training, and so previously with DDR4 and earlier, we had a known phase relationship. For memory, in order to perform our transmitter testing, we need to make these tests based on a read or a write burst. And the known phase relationships does not exist the same way it does previously. So the test tools need to be more intelligent in that regard. Timing is also a bit of a challenge. So as you scale in frequency with memory, your data valid window shrinks. So margin is shrinking, and we need to recover that somehow through different timing parameters, and that's where jitter comes into play. So there's new jitter tests, which I'll explain in the next slide. And finally, perhaps this is the most interesting and dominant feature that will really make or break the success of DDR5 as we move to higher speeds, and that's the impact of equalization in a DRAM circuit, which traditionally has been very basic and simple, and now we add something more complex as equalization. So how does a designer test to that? That's something we'll cover briefly here. For the TX specs, as I mentioned, static timing analysis really doesn't cut it anymore. We need to look at more of a jitter distribution model and how to reduce how to quantify, and then of course reduce the impact of jitter. So we have things like data, strobe, and input clock jitter that are bounded by random and deterministic components. This is not anything new for the industry, but for memory, it's a little bit different because we have an externally clocked bus that is referenced. Data jitter analysis is based on a externally clocked strobe. So this is something that going forward definitely will not go away and will be with us for quite a while. Now don't forget with memory, when you're making those measurements, half of the job is just getting access to the signal. So here I'm showing an example of a new probe that was recently introduced. This is the MX series probes, which doubles the bandwidth from 13 gigahertz up to 25 gigahertz. And as you can see on the image on the right, we're soldered down onto a memory BGA component interposer, and the width of this, the pitch of this probe is half the size of previous generation. So now we can essentially attach twice as many probes in the same space as before. It's very common for memory applications to require these specialized component fixtures called interposers. And what this does is it allows you to access signals underneath the DRAM package, which before are impossible to connect to because they're underneath. So we remove the DRAM part, install the interposer, and then put our BGA package on top. So this is also a necessity going forward. So we need to consider how to de-embed and optimize around noise to make the most accurate measurement as possible. Going forward, something that's new that has existed in industry for quite a while is this idea of receiver testing. And I want to highlight a couple things that makes this uniquely different from memory. So first of all, memory, it's wide, it's a parallel bus, these signals are single-ended, they're bursted. So we need to take that concept, that architecture, that system design, and apply that in a manner that fully represents a receiver test that we can calibrate to and repeatably test to. So for that, of course, there's a lot of system impairments that we need to incorporate, and something that's new that's been developed to enable this is a new test fixture. On the bottom right here, this is what we call the CTC2, or channel test card. And this exposes and breaks out, routes out all the necessary high-speed signals, all the DQ signals, all the DQS clock, and control signals like reset and alert. Those are signals that we can calibrate to using an automated calibration software. This will apply the limits per the specifications and make this receiver testing much more easy to implement. And I think what's, the main takeaway from this is we've really gone away from direct probing measurement at the far end of the channel to now the measurements are referenced instead of at the ball of the part. Now they're on die, they're in circuit on the receiver because of this DFE equalizer that's now part of the specification. And that DFE equalizer has been incorporated into the receiver test as a model for calibration. So how does this work? How would one actually go about making this test setup? So here's a M8020A BERT, and we have in yellow, this is our data lanes, and green is our strobe. So like I said before, this is a externally clocked source synchronous interface. We have data coming into the fixture, going into our receiver, and that is then looped back out as the thick green and yellow lines going back into the BERT. And that's how we make our bit error rate test for DDR5 receiver test. Now let me switch gears a little bit, go up the stack, if you will. I've talked about transmitter test, some of the new jitter measurements, the probing that needs to be optimized for higher speeds, receiver tests now with a BERT, incorporating DFE into the calibration and making the measurements DFE aware. So let's move into more of a system level integration, system level design and analysis. This is where a logic analyzer comes into play. With the right software and probing and interposer solutions, one can basically decode all the commands organized by rank and bank. You can look at your data rate performance by analyzing specific read and write transactions. Maybe you want to study long-term refresh rate statistics, self-refresh versus direct issued refresh commands. Maybe you want to analyze mode registers and look at the mode register settings as the system is booting and training and initializing. But I think most of all, what a lot of us care about is, how much margin do we have in our design? Are we meeting the JEDEC timing? And this is what this view is all about. Again, the mechanics of how do we physically connect up. This is a very important part of the overall solution. There's essentially three parts to this. There's a DIMM interposer, which would expose and provide more access to more of the signals. So all of the command address and data signals. We have different form factors depending upon the flavor: registered DIMM, unbuffered DIMM, SO-DIMM. Or if you're more concerned about a component specifically, we have BGA interposers that are available with these fan-out wings for routing the signals out to the logic analyzer. And then lastly, for more of an in-system debug, there are also our mid-bus probes, and of course this takes advanced planning because you need to put a footprint for this specific probe type on your board. You need to lay this out beforehand. And lastly, just to kind of summarize the protocol view, how this comes together. Again, there's kind of three parts to this. There's the hardware itself, the logic analyzer module. The most common one is the U4164A. This has the highest performance that's catered just to DDR5. We have some of the probing solutions that I mentioned earlier. The FS2600 is the more common one for RDIMM and LRDIMM applications. And then lastly, the B4661A analysis software that runs on top of the logic analyzer. So with that, I will close out my presentation about memory, covering transmitter, receiver testing, and of course, protocol. And I'll look forward for more questions later on, and I'll pass it back to Steve.
Thanks, Randy. Looks good.
All right. So my discussion here is going to be a discussion around some of the intricacies of data center work that's happening in standards as well as deployment. As Brig mentioned a bit ago, we see data centers now measuring power consumption by the square meter, and there's a lot of focus on getting power reduction or power increases under control. It seems like invariably the power always seems to be going up, and also increasing IO density. And it's the issue of IO density and indirectly power consumption that we'll talk about here over the next couple of slides. So just by introduction, my name is John Calvin. I'm a planner in Brig's team. We cover the IEEE and OIS standards, as well as a number of other technologies related to data center physical layer validation. As Brig indicated, I'm out here in a standards meeting now, and this is what we do. I mean, we try to make sure the standards don't go off into the weeds and build specifications that can't be tested. And in that regard, we are your best advocate to make sure that these standards are testable and have well-defined interoperability requirements, which is what we really do. That's our major contribution to these standards and technologies. This slide kind of gives you an overview of where we've been and where we're going and where we are today. The blue dotted line here is circling around where we are today, and it's centered around 802.3 CK, which is 106 gigabits per second. That's 53 gigabaud PAM4. It comes in a chip to module, chip to chip, a cable, and a backplane interconnect, and is generally known as 400 gig Ethernet in some of the vernaculars here. A companion standard to IEEE is the OIF CEI 112 gig VSR PAM4 specification. It runs at a slightly different rate, it's a little bit faster, and it's typically used for very short reach, and it's the interface of choice for optics. So both of these standards have a place in the ecosystem, and we're finding that we're needing more and more specialized specifications to really address the unique aspects of these technologies. And I'll go into more detail there in a moment. But coming up next, though, we see the 802.3 DF and the 224 gig technologies. And these technologies are important because these are the next technology rollout in the next speed doubling that we'll see, and it's coming on a faster cadence than what we've seen in the past. These specifications are well underway, and we're not even done with the 100 gig specifications yet. The drive and the need for better throughput and higher IO density is enormous, and that's what's driving these two forward-looking standards here that are in their early stages to get us at 200 gigabits per second per lane. These will be 106 or 112 gigabaud PAM4 technologies. And you think about that for a minute, this is not that far away. This is at most 3.5 to 4 years away. And any buying decisions that you make with regards to instrumentation in your lab should be done with a 5-year horizon kind of perspective, or rent the equipment in the interim if you really want to focus on the here and now, because the instrumentation for the next speed grade might be a better version of the same product. So these are considerations that you want to keep in mind here when you're settling on your instrument choices, and these are substantial choices to realize. These are very expensive instruments, and they represent a significant portion of a company's capital. If I drill into the standards that we have today, we have a variety of technologies, and as I alluded a moment ago, you see a bifurcation of these specifications really geared towards unique and specific lengths. So we have the full portfolio of our optical specifications, as well as the electrical specification designed to drive the optical modules. We start off with 802.3 CK. This is the electrical interface of choice that IEEE is defined. And then we have supporting optics, and actually also supporting, in some cases, coherent interconnects, which we won't talk about in this slide deck. This slide deck will be focused primarily on direct detect technology. But the optics for 10 kilometers, or 50 meters, or actually this is 500 meters, or 80 kilometers are all different technologies. And they have different physical requirements, signaling requirements, and they have separate standards to support those. In the OIF community, we have, standards here that are designed for multi-chip modules, extra short reach interfaces. The XSR Plus specification is new. This is actually the interface or interconnect choice for near package optics. We have VSR, which is probably the most prominent specification in the OIF community. A lot of people are following the VSR spec. We have medium reach and LR specifications as well. The most recent introduction has been the co-package optics specification that's come out of OIF, and that was just formalized last fall, actually December timeframe, and it's coming together quite well. So the point is, there's lots of specifications, and you need a test partner that will help you understand the test requirements and to track these standards, because there's a lot happening under the surface here. This is a snapshot of some of the common test points, and we're going to get into some of the specifics of physical layer validation now. We're going to go and dive into the the electrical portion of the specifications for 802.3 CK as an example technology. The same things, the same issues fall out of VSR as well. And this is the same technology that you'll see advancing to 224 gigabits per second, just in roughly 3 to 3.5 years. This is all measured at 100 gigabits per second per lane today, and it's typically aggregated in by 8 configurations or by 4 configurations. There's a couple of key subclauses in the specifications. One is a chip-to-chip specification. This is obviously, if you're trying to talk between silicon, you use chip-to-chip interface. There's a chip-to-module interface, which is known as C2M. This is an interface that is used to talk to, the QSFP port in the back of a switch or a router, for instance. Anytime you want to go to a modular interface, which is the most common interface in the standard, you'd go to the C2M specification. And what you would actually measure and how you optimize your measurements is very different depending on which one of these measurement clauses you're after. It's important to keep these straight, and one of the things that Keysight does is it provides you a fully automated test tool that helps you organize your measurement list and provides and executes the right measurement science, the right bandwidth requirements, whether it's a Butterworth or a Bessel-Thompson. All these measurements and considerations are taken into account in an automated system for you. These are the test points that you'd see in a pictorial diagram with the red circles around them, and then they're translated up here to a typical module compliance board or a HCB, host compliance board here, or breakout. And this is a solution that we partner with Wilder with, and they have outstanding electrical properties that follow the IEEE specs to the letter. And we use them as part of our conformal test tools when we do our testing and when we evaluate and build our tools. One of the big things that's happened here in the specifications here as we went to 100 gigabits per second is really refining the reference equalizer that you'll find in the silicon. Now, this is a block diagram that we show down below here where we have clock recovery aspects. There are unique clock recovery aspects that you'll find in the 100 gig specifications around something called a Muller-Muller. We have random noise injection or requirements known as input referred noise. We have continuous time linear equalizers, and we have decision feedback equalizers, all working in concert here to get a BER anomaly of 1e to the minus fifth. Note that these errors, these links are not error-free by a long shot, and they relies on forward error correction to really make these links operational at the required 1e to the minus 13 that's mandated by data center applications. This is a nice snapshot of a Muller-Muller in action. What it does is the combination of the Muller-Muller gives you a clock recovery, and it also works in concert with a decision feedback equalizer to give us a sample point in the middle of the UI known as T sub S. And around T sub S is where all your measurement performance or measurement actions occur. In this case here, you can very faintly see the T sub S label across the top of the screen here, and you can imagine drawing a line down through the middle of the eye diagram. In this case here, we're going to perform something called a vertical eye closure calculation, and we're also going to evaluate eye height. We're going to do jitter calculations and things like that. But we're only going to do this after we've optimized the decision feedback system and the CTLE to get optimum performance. Now, the process of actually getting this optimum performance is quite challenging. We've actually done some work in this area. Presently, the state-of-the-art mindset is you extract the pulse response from your signal, you feed it into COM along with a couple other parameters that relates to the signal properties that you measure, and then COM will actually rapidly search through the entire grid solution space and tell you what your CTLE coefficients or gain settings should be and your DFE coefficients should be. And we found that this is actually the best way to actually provide the optimization of these otherwise very complicated equalization problems. I mentioned a moment ago the business of input referred noise. In the standards today, there's an effort to really make sure that the simulation space and the physical layer measurement space converge at a common reference point. And in some cases, IEEE has done a great job at this. In other areas, there are some gaps. But one of the things they wanted to do to make sure that simulation tracks real-world measurements is to incorporate a noise floor in the instrumentation. So what you see is a one-sided noise spectral density measurement. This is a parameter known as eta 0. And it's set here to 4.1 e to the minus 8 gigahertz per or volt squared per gigahertz. And if you evaluate that over 40 gigahertz Bessel-Thompson response, which is what you normally would do, that translates to about 1.2 millivolts RMS, which means that if you are doing this correctly and you feed in a flat line into your instrument, it should measure 1.2 millivolts RMS. And the Keysight tools have been modified to enable you to control this one-sided spectral density through the injection of synthesized noise. In the case of our DCA, our sampling architecture operates well below this noise floor and has to add noise in order to reach the requirements of the reference equalizer, reference receiver. So you see the random noise being injected here. You can turn it off if you like, or you can increase it if you want to do margin tests. And then similarly, on a real-time scope, we have a bit of the opposite problem. On the real-time scope, we have to back the noise off through some noise management exercises here. The real-time scope has a higher noise performance than the equivalent time scope does. And what we do is we go through and carefully evaluate the noise floor at different levels in the PAM4 signal here. We have the thresholds and the levels here that occur at level 0, 1, 2, and 3. And we extract these numbers and we incorporate the noise parameters into our measurement system. So we actually take into account the slew rate of a signal, and we back out the corresponding noise if, for instance, you're on a 0 to 3 transition or a 0 to 1 transition. And the noise that you would extract is different depending on which transition you are traversing. This is a great example of a typical PAM4 signal. It shows an eye diagram here, which is characteristic of the IEEE signals. The signals are completely hammered, they're closed. And you know, we can't go through and equalize the losses out of these measurements, because if you do that, the zero forcing function that comes out of equalization pushes your RJ up to unacceptable limits. So it'll never pass your RJ thresholds. So what we do is we've rewritten a lot of our jitter algorithms to operate on closed eyes. And you can see that at work right here. This is a setup that we did just last week, and it's exciting because it brings a lot of new elements to the table here. As we were mentioning a few slides back, error rates now are inherently somewhere in the ballpark of 1 to the -5 BER. And really measuring the raw error rate is irrelevant for most designs. What people want to see is what is the frame loss ratio. And frame loss ratio is tough to do because it takes the FEC engine to be fully functional and striping data across multiple lanes. And that's hard to do when you're testing this a single lane at a time. So in this test setup right here, we're showcasing a couple of new things. Most notably on the left-hand side, we have something called a G800, and this is a instrument that comes from our protocol group here. And the G800 is capable of actually generating BERT traffic over a QSFP-DD interface or an OSFP interface to fully light up and energize all the lanes of a fiber. And we can choose to put a PRBS 31 or a PRBS 13, whatever we want, we can put on the adjacent lanes. But in this test setup, we inject a PRBS 13Q across one of these fibers under test, and then we run it into the combination of the DCA to validate its electrical performance, or back into the generator here to verify its frame loss ratio. Now we're taking this instrument in the center. This is an M8040 BERT. When we're generating a precision impairment, so we take one lane out of the 8 and we generate the absolute highest allowable RJ. We basically do what's called a TP1A calibration, and that brings all the physical impairments to the maximum limit, and we feed that in on one lane, and we can observe the shape of the forward error correction tail that comes out of this. And then the DCA or a real-time scope could be used on this side for your calibration process and or signal TX validation process. This is an example of effect tail I was talking about a moment ago. You see here that in a system that has a non-impaired channel, that it's operating, you know, most of the bits are coming across with 0 errors, and you can see the error distribution, the number of frames that it picked up with, or code words that it picked up with a single symbol error is 800,000 in this case, and with 2 errors, it progressively gets lower and lower until we see that there's really nothing happening below, say, well, really nothing below 4 symbol errors per code word. And this is actually an example of a device that has excellent frame loss ratio margin, because the marginal limit is 15 errors. Once you get to 15 errors, the entire frame gets discarded. So it's the distance from the 15 error threshold as well as the shape of this distribution that people and the designers really care about. In the case of the lane that's been impaired right here, you can see that its error ratio is actually quite a bit higher. It's not operating at the same level of performance as its neighboring lanes. And you can see the errors actually continue well down into the frames, down as low as 2 symbol errors per frame. So you can see in this case here, we're only three symbol errors away from a total failure of a packet. But this is good because this is under full impairment. This is as bad as impairment would ever get. You're verifying that your receiver and your transmitter all operate under these conditions. If you had a system that was operating down here below 15 symbol errors, you realize that you're now losing packets due to a physical layer design problem. And this kind of insight is actually quite hard to get. And this is one of the first tools that really brings all this together with good physical layer evaluation tools and frame loss ratio tail analysis. The two instruments that Keysight really offers in this space are different in many sense, but they're both oscilloscopes and they both have the bandwidth requirements. If I look at our sampling scope on the right-hand side, this is our DCA. It's going to have the best noise and bandwidth capabilities. It does this with a 16-bit A to D, and if you're going to be doing TDR or looking at optical signals, this is probably your platform of choice. It's going to give you the best results and the best answers. And in the communication space, this platform is known as the gold standard. So this is really the go-to platform for all communications related work. But a lot of the technologies that people are dealing with now have adjacencies into PCI Express. And you can't do PCI Express with a sampling scope. So in this case here, we bring the UXR instrument. This is 113 gigahertz UXR into the mix, and we solve the same measurement problems and measurement science issues on the UXR platform. And this is our native platform for error detection. It does all the things related to physical layer validation that the DCA does, and it has a few other capabilities in terms of things like phase noise analysis, and it has native clock recovery that gives it a unique ability to measure signals with 224 gigabit per second capabilities, which there are no physical clock recoveries for today. This is a snapshot of our solution space, and on the right here you can see an example panel of all the measurements you'd want to do. Typical full physical layer conformal test set constitutes about 120 measurements. And the prospects of getting these right and configuring these by hand is a pretty big burden for any test engineer. So these are the tools that make the repetitive nature and just the familiarity with the specification a lot easier, because we encapsulate all that into a compliance tool for you. These are the current standards. We have the 802.3 CK and the 112 gig VSR specifications, but not uncommon to see we have support for all our older standards going back to, in some cases, 2.5 gigabits per second. And we have continuity all the way up to 112 gigabits per second. This is a snapshot of our portfolio. And closing here, we have a new platform here, a M8050 Bird, that is actually will be following in the same legacy of our M8040 Bird. It's got the platform that can support our 224 gig signal generation better than anything else in the market right now. So this is a very high powered Bird. This in combination in concert with our UXR for error detection and our DCA for its signal integrity make a set of tools here that are essential for any kind of data center validation activities. All right, with that, Steve, I'll give it back to you. Thank you.
Thank you, John. Actually, what we're going to try to do is my partner in crime, Madison, is going to see if she can get it running for us. So, Madison, I'm passing over to you.
All right, thank you, Steve.
Hi, my name is Rick Eads, and in this section of the webinar, we'll be talking about PCI Express technology. We'll be going over some of the requirements for testing PCI Express at PCI Express Gen 5 levels, and then we'll talk a little bit about what we'll need for testing PCI Express 6.0. What you see here is a vintage chart that shows the different revisions of PCI Express technology through the years. And on average, the PCI SIG has released a new version of the specification about once every 3 years or so. Now, the exception to that has been with PCI Express 5.0 and PCI Express 6.0. In this case, or in both of these cases, the PCI SIG has released new versions of the specification, effectively doubling the performance of PCI Express technologies about once every 2 years, as opposed to once every 3. Now, there's a couple of reasons behind this, and I think mostly the reasons why you see a significant decrease in the timing between different revisions of the PCI Express spec have been due to improvements in speed at which the hyperscalers and cloud service providers have built out data centers, and the tremendous growth that we've seen in the use of artificial intelligence and other expansions in server technology. To help you along your path for developing your PCI Express products, Keysight Technologies offers the broadest array of tools available from any test and measurement vendor for supporting PCI Express development. And these start with analysis tools with our PathWave ESOF simulation tools. We also have vector network analysis and software with our PLTS platform for doing channel analysis. Then the heart of the Keysight solution, represented by the UXR family of oscilloscopes with bandwidths up to 110 gigahertz, coupled with our bit error ratio testers in the M8040 BERT, which is capable of not just NRZ testing, but also PAM4 testing. And newest in our lineup is the protocol test tools for PCI Express Gen 5, which will be supporting PCI Express, CXL, and have a roadmap to support PCI Express 6.0 as well. Here you see a basic setup for testing a PCI Express transmitter. And in this case, we have a breakout board where we are testing silicon. So this is a case where we're testing an ASIC, for example. And you can see that the transmitter of the silicon is connected to the inputs of the Keysight UXR series oscilloscope, and then we're using software to do an analysis of the transmitter. So the basic setup for transmit testing consists of some type of breakout board or fixture with the signals going into the oscilloscope, and then we have a number of different software tools that we might use that we'll talk about a little later for doing analysis of those signals. On the receiver test side, the testing is a little bit different compared to transmit test. The goal for receiver test is to be able to present to your receiver a worst case signal to determine whether or not your receiver is capable of operating with a bit error ratio that meets the target of PCI Express, of the PCI Express spec, which is 1 error in 10 to the 12 bits. Now to do that, we have to effectively emulate that worst case signal, which represents a minimum I width and a minimum I height with a certain number of impairments. The PCI Express specification is referred to as a die-pad to die-pad spec. So what we have here is a representation of a far end or a worst case scenario for channel loss combined with worst case nominal impairments that are injected into the signal to represent the kinds of impairments that that signal would see in practice or in the field inside of a real system. So we have on the left side a number of those impairments identified as RJ, SJ, differential mode and common mode interference, which are injected into the signal that's coming from our pattern generator in the BERT. Those signals are then pass through a variable ISI channel that provides us with most of the impairments that we believe are effectively compensated for through equalization. And then to calibrate the final I width and I height, we add a package model and then also apply a reference equalization scheme. This gives us a target I width and I height for the signal that we'll be presenting to the receiver, and gives us a good sense of how that receiver will behave when it might face a similar type of impaired signal in the field. Often I get asked how much bandwidth would I need for an oscilloscope to be able to do PCI Express 5.0 testing or 6.0 testing at 32 gigabaud. So what you see here is a representation of a PCI Express 5.0 compliance signal being driven by our M8040 BERT and put into 110 gigahertz oscilloscope platform. Now you don't need 110 gigahertz for PCI Express, but to do this experiment, I wanted to look at what the frequency domain content was of the signal. And you can see that beyond about 64 gigahertz, there really isn't much in the way of spectral content that we would need to be concerned with. So for testing purposes, the PCI SIG decided that a good bandwidth minimum for PCI Express technology testing would be 50 gigahertz. And this becomes really important when you're doing that calibration for the BERT output that we talked about in the previous slide, where we want to be able to calibrate the BERT output. because that's where you would expose the oscilloscope to the full bandwidth of the PCI Express spec when it's operating at 32 gigabaud, and you would see signals like this. So we specify a minimum bandwidth of 50 gigahertz. A recommendation from Keysight would be to have 59 gigahertz if that's within your budget. One of the common form factors for PCI Express technology is the card electromechanical form factor, or CHEM connector. And what you see here is how we test a system motherboard through its CHEM connector with a compliance load board test fixture that's provided by the PCI SIG. So we connect the CLB to a real-time oscilloscope using a cable, and then using a tool such as InfiniSim from Keysight, we apply an S4P S parameter file that adds additional losses that are necessary to complete that die-pad to die-pad measurement requirement that is defined in the PCI Express test spec. The card electromechanical form factor for PCI Express 5.0 is probably the most commonly deployed form factor, but there are others consisting of M.2 and U.2. What you see here are the compliance fixtures available from the PCI SIG, which represent testing of add-in cards on the left side with the compliance baseboard, and then we have the two different compliance load boards that are used for testing lane lists from by 1 up to by 16 in a card electromechanical slot of a motherboard. To help you in speeding up your validation of your PCI Express 5.0 device, Keysight offers a transmitter tool validation software package called the D9050 PCIe, and this allows you to do validation of both chem spec and base spec requirements for your PCI Express device. So for example, if you're doing silicon, you can use the base spec test. If you're doing a add-in card or motherboard, you can use the chem base test, and this does all the testing of your presets. It does your jitter test. It does the requirements necessary to pass the compliance tests at workshops. And when it's finished, it'll produce an HTML report that you can either print or save as a PDF file, and you can also save the results to a CSV file, which is very convenient. I did want to close with a few words about what's coming, and that is PCI Express 6.0. So one of the big changes of PCI Express 6 versus PCI Express 5 is, of course, the move to PAM4 technology, or pulse amplitude modulation. So in this case, we'll be transmitting 2 bits per symbol instead of 1 bit per symbol, which is associated with Gen 5 and NRZ encoding. The tools necessary for doing this testing are very complementary to what we have for PCI Express 5.0 and represents the next step in the evolution of PCI Express technology. I wanted to close my presentation with this final point, and that is that the tools that Keysight offers for testing Gen 5 and Gen 6 are essentially the same. And this is done on purpose because we believe that it's important to be able to offer you tools that are extensible from one technology to the next, because the tools are going to represent a significant investment on your part, and also that these tools will be usable for not just PCI Express Gen 5, but also with PCI Express Gen 6. And again, a reminder that Keysight offers the broadest selection of tools, from doing simulation to physical layer test to transmit and receive test and protocol layer test for PCI Express.
Thank you, Rick. And thank you, Madison, for getting that running for us. And I think we're at near the end of our session, so we have time for some Q&A. And while we wait for questions to come in, we don't have any questions just yet. I'll remind everyone that in the handout section of the webinar, we have all of the slides that were presented today, so that you can grab that and before we leave the webinar and close everything up. But I wanted to thank everybody, and especially thanks the audience for your patience. We did have some technical difficulty there and got it sorted out finally. But as we wait for our any questions that are coming in.
That's the beauty of a live performance, Steve. So well done.
And thank you, John, for helping us out with the decision-making process. That was a big help, because we were able to finally get it running.
Proof that we were not pre-recorded.
Yes, exactly. Don't see any questions coming in, so I think that's going to be the end of it. Thank you to Brig and Randy also. We appreciate the input, and of course, Rick, thank you for your presentation. And again, Madison for helping out. And then at the end of the webinar, we do have a little survey for you to take on when we exit. And I think that'll do it for us for today. We're right at the top of the hour. And so thank you all for joining us today, and thank you for coming. So thank you for the panelists too. We realize that that was a lot of extra time in your planning and presenting and getting that thing running for us. So thanks everyone for coming.
Thanks, Steve.
Thanks,
Thanks,
Steve.
Madison.
All right, bye-bye.
Bye.
Bye, everyone.
Bye.